Hello and welcome. Today we're going to be talking about PDE problems with sources. So when you have sources, what you have essentially are non-homogeneous components to your PDE. So your solution methods are going to have to be different. Because recall, the separation of variables applies only to homogeneous problems. Okay, so that's problems where there's no sources and the boundary conditions are homogeneous. So let's look at a new problem. I'm going to give you one problem here. It's going to be this one. So it's going to be a heat equation. And it's going to be UT is equal to UXX plus 1. So right here, there's a source. So it's going to be a uniform source. So the idea here is, and this is going to be over the domain 0 to 1. Okay, so a really straightforward domain. And what we're doing here basically is applying some heat. So I can kind of represent it as like basically putting a flame underneath this metal rod. Okay. The next thing we're going to do is we're going to look at a specific set of boundary conditions. So the boundary conditions are also going to be non-homogeneous. So it's going to be u of 0, comma, t is equal to 1, and u of 1, comma, t is equal to 1/2. Okay, so those are boundary conditions are non-homogeneous. Okay, all right, so we have two things here that make this problem impossible to solve with separation of variables. So I'm going to tell you now what the trick is. So the approach is to break the solution into homogeneous and a non-homogeneous parts. Okay, so the homogeneous part so here with the non-homogeneous parts, what we're going to do is say u of x comma t is actually equal to w of x comma t plus u eq of x. So those are the two parts. And the homogeneous part, that's going to be equilibrium. That'll be an equilibrium problem. I'm sorry, this is the non-homogeneous part. This is going to be an equilibrium problem. All right, so the homogeneous part, that will be time dependent. All right. So we can see here that has the time dependent, so that's going to be the homogeneous. While the U equilibrium, that's going to be the non-homogeneous. Okay, so let's see if we can break this one down and do the idea here. All right, so to do that, so let's solve for W. So what we have to do is we have to homogenize the PDE. All right, so we had UT is equal to UXX plus 1, and we had the boundary condition U of 0, comma t is equal to 1, and U of 1, comma t is equal to 1/2. All right, so we're going to homogenize. So now we're going to call it W of t is equal to Wxx. So essentially what we're going to do is we kill off the non-homogeneous source term, okay? The next thing we do is we're going to homogenize the boundary conditions. So we're going to do 0 comma t is equal to 0, and W of 1 comma t is equal to 0. All right, so that's our homogeneous equation. We can solve via separation of variables for W. All right, so this is a very standard heat equation. We can actually find the solution. Here's the general solution. It's going to be, because we have basically zero temperature boundary conditions, we have a specific solution. It's going to be the sum, starts from n equals 1, goes up to forever, of e to the negative n pi quantity squared t times sine n pi x. And that's because, of course, w is of x comma t is going to be p of x times q of t, and we have Pn of x is going to be equal to the sine eigenfunctions, and that's owing to the fact that we have a zero temperature boundary condition, and a lambda n is equal to negative n pi quantity squared. All right, so those are our eigenvalues. And of course, our Qn of t equation is going to be e to the negative lambda n comma t times, oh, I forgot one thing. We forgot our Bn coefficients, So the Bn are going to be our free parameters. And these, of course, are going to be determined by the initial condition. So we'll hold off on figuring out the initial condition. In fact, that's going to be a little bit more tricky than we've normally done so far as well. But the idea here is we have this solution. So let's now go with it and now start the next process, which is now solve the non-homogeneous equilibrium solution. So here we had ut is equal to uxx plus 1 with boundary conditions there. All right, so now we're going to do equilibrium. So we're going to set ut is equal to 0. And now we have ueq of x, right? I'm just going to call this u of x just for simplification. We can bring it back later. I'll call it ueq. I just don't want to have to keep writing eq every time. So what we have is 0 is equal to uxx plus 1. I like to move things over to the other side like that. All right, and now, of course, I can integrate, and we get ux is equal to negative 1, negative x plus c1, okay? And then we integrate again, and we get u of x is equal to negative x squared over 2 plus c1 x plus c2. So that's this is our EQ, our equilibrium solution. All right, so now we just have to use the boundary conditions. We have to use the boundary conditions to determine C1 and C2. All right, so UEQ of 0 is going to be equal to 1, which is equal to, well, now we have to evaluate our equilibrium solution at 0, so we're going to get C2. Okay, so that's just plugging in x equals 0 everywhere. right? And then UEQ of at 1 is going to be equal to 1/2, which is equal to negative 1/2 plus C1 times 1 plus 1. Okay, we can solve this one. And this is our equation we have to solve. I'm going to move the negative half over to the other side. So we're going to have 1 is equal to C1 plus 1. And we see that the ones, sorry, this should be an arrow there, not an equal sign. That those will now cancel, which means that C1 is equal to 0. All right, so that simplifies things pretty good. So our equilibrium solution then is going to be negative x squared over 2 plus 1. All right, so now we have our two things, and now we're going to put them back in. So now the next step, like in every kind of linear algebra problem, if you solve these different components, then you just add them all together at the end. So you have U general solution is going to be x comma t, which is going to be equal to W of x comma t plus UEQ of x. So let's just write that down on the next page. So what we have here is U general solution of x comma t is going to be equal to W of x comma t plus UEQ of x. And I can rewrite that as the sum. N goes from 1 to up for forever, e to the negative n pi quantity squared times t times sine of n pi x plus, so that's our, we have to have our bn parameters in there. And then we have 1 minus x squared over 2. All right. So that's our general solution. So what's really important is, I'll just say this, is the next question we have is, of course, okay, what are we going to do about initial conditions? So in general, so that's our question. What do we do so in general, you're going to have a u of x comma 0 is equal to f of x, right? So this is some given function. Well, we can just do that. So set t equals 0, and we're going to get f of x is equal, so we're going to set t equals 0 up here and get the sum, bn. Our exponentials go away because they turn into 1 when t is equal to 0. Like that. Plus, we have to remember that we have this equilibrium non-homogeneous solution sitting right there. Okay. All right, so the question then is now, how do we determine the bn's? Well, the answer is, of course, we have to move UEQ over to the other side of the equation above. So we get f of x minus 1 plus x squared over 2. So that whole thing is now equal to the Fourier sine series. All right, so now the bn coefficients are going to be 2 integral over 0 to 1 of f of x minus 1 x squared plus x squared over 2 times sine n pi x dx. So what this says then is that, of course, the Fourier coefficients are for the initial condition f of x minus UEQ of x. So that's what the Fourier coefficients actually represent. They don't represent f itself, but rather a modified version of f. All right. So with that said, now let's go and sort out one more of these. So let's actually look at a specific example. Let's give an initial condition. And our initial condition has to be, I'm going to make it actually pretty straightforward. It's going to be 2 minus 1/2 x squared. That's going to be my f of x, all right? So this is what I would call a very convenient initial condition because it simplifies our work. But that's important for examples. We should look for examples that do things in a really straightforward way, especially for a first example. All right, so we can do it. So our problem was f of x minus ueq of x is equal to that sum bn sine n pi x, n starts from 1 and goes up to forever. Okay, so now we can write these in here. That's going to be 2 minus 1/2 x squared, and that's going to be minus 1/2 x squared plus 1. We can see, of course, that that cancels with that, and 2 take away 1 leaves just 1 behind. All right, so we have to find the Fourier series, the sine series of 1. All right, well, that's pretty straightforward to do. The bn's are going to be equal to the integral 2 times 0 to 1 of sine n pi x. Of course, we're multiplying everything by 1 there, dx. That's going to be cosine of n pi x all over n pi. Okay, now of course we have to make it negative, right? And then we're just going to multiply by 2 there, and then we're going to evaluate at 0 to 1. Should be pretty straightforward. So we have 2 times 1 minus cosine of n pi all over n pi, which is also, we can express this way, 1 minus a minus 1 to the n power all over n pi. All right, so clearly this so this is going to be, so it's going to be 0 when n is even, and it's going to be equal to 4 over n pi when n is odd. All right, so what we can do then is actually say that n is equal to 2k minus 1, and say k is going to be equal to 0, 1, 2, 3, 4, and so on and so forth. And that just simplifies our work a little bit. So what we're going to get then is the following. So u of x comma t, our final answer is going to be, of course, minus 1/2 x squared plus 1. That's my ueq of x, right? Plus the sum, k goes from 0 up to forever, of 4 over 2k minus 1 times pi times e to the negative 2k minus 1 times pi quantity squared t times sine of 2k minus 1 times pi times x. All right, so there is a final answer that looks pretty good. Let me check. Did I get this right? I think I got it right. So when n is even, then we'd have 1 minus 1, so yes, we get 0. And when n is odd, we get a minus 1, which becomes 1, plus 1 is 2, times 2 is 4. So yes, we really do get that. All right, so that's our final answer. That's putting everything together, and this is going to be my W of x comma t. So that's a really cool problem. It has everything in it, and it even had a very simple Fourier coefficients to compute. So I hope you enjoyed this problem. We'll do more in the future. Thank you so much.